Alright, so in today's video, we're diving into the world of ultraviolet spectroscopy, or UV-Vis spectroscopy, a powerful technique used in chemistry to study the electronic structure of molecules. We'll explore how UV-Vis spectroscopy works, the concept of electron transitions between molecular orbitals, and the significance of conjugated systems. By the end of this video, you'll have a solid grasp of the principles behind UV spectroscopy and its practical applications in organic chemistry. Let's jump right in. Alright, so let's start with the basics. Ultraviolet spectroscopy, often referred to as UV-Vis spectroscopy, is a technique that measures the absorption of ultraviolet light by a chemical sample. When UV light passes through a sample, certain wavelengths of the light are absorbed by the sample, depending on its molecular structure. This absorption is directly related to the movement of electrons between different molecular orbitals. The data from UV-Vis spectroscopy is typically presented as a plot of percent transmittance or absorbance versus wavelength. What we're really interested in here is how much light is absorbed at each wavelength, which gives us clues about the electronic structure of the molecule. So, why does a molecule absorb UV light? It all comes down to electron transitions. When a molecule absorbs ultraviolet light, electrons are promoted from a lower energy molecular orbital, specifically the highest occupied molecular orbital, or HOMO, to a higher energy molecular orbital, the lowest unoccupied molecular orbital, or LUMO. The energy difference between the HOMO and LUMO determines the wavelength of light that the molecule can absorb. The smaller this energy gap, the longer the wavelength of light the molecule will absorb. This means that if the energy gap is small, the molecule will absorb light at a longer wavelength and lower frequency, which is key information we can derive from a UV spectrum. Alright, so when we look at a UV spectrum, what we're really seeing are the various wavelengths of light that a molecule absorbs as electrons are excited to higher energy levels. The key feature we focus on is the wavelength of maximum absorbance. This tells us about the extent of conjugation within the molecule. The more conjugated a molecule is, that is, the more alternating double and single bonds it has, the lower the energy difference between the HOMO and LUMO. This results in absorption of longer wavelengths. So, if you see a molecule with a peak at a longer wavelength, you can infer that it has a significant amount of conjugation. Let's talk a bit more about conjugation. Conjugated molecules have unhybridized p orbitals that allow for the delocalization of electrons across multiple adjacent atoms. This delocalization reduces the energy gap between the HOMO and LUMO, meaning these molecules can absorb light at longer wavelengths. Take benzene, for example. It's a classic case of a conjugated molecule with three broad absorbance peaks in its UV spectrum at around 180, 200, and 255 nanometer. These peaks correspond to electronic transitions between different energy levels in the molecule. The extended conjugation allows benzene to absorb at these specific wavelengths, which are in the ultraviolet range. Larger conjugated systems, like those found in certain dyes or organic pigments, can even absorb visible light, which is why they appear colored to the human eye. This principle is why UV-Vis spectroscopy is sometimes referred to as UV-visible spectroscopy. So, how is UV spectroscopy actually used in practice? It's a crucial tool in organic chemistry and biochemistry for studying molecules with conjugated systems, like aromatic compounds and biomolecules such as proteins and nucleic acids. For example, UV-Vis spectroscopy can help determine the concentration of a protein in a solution by measuring absorbance at a specific wavelength. It's also used in the pharmaceutical industry to verify the purity of compounds and identify substances based on their absorption spectra. Additionally, because certain drugs have characteristic UV absorption spectra, this technique is invaluable for monitoring reactions and studying the interaction of drugs with biological systems, making it a staple in both research and quality control settings. Alright, so to wrap things up, UV spectroscopy is a powerful analytical tool that allows us to study the electronic transitions of molecules and understand their structure and conjugation. We've covered how this technique works, the significance of electron transitions and conjugation, and how these principles apply in real-world scenarios, from scientific research to pharmaceuticals. If you found this video helpful, please give it a thumbs up, share it with your friends, and don't forget to subscribe for more chemistry content. And if you're on the King of the Curve app or web app, make sure to leave a like and let us know in the comments what topic you'd like to see next. Check out the app for more in-depth material. Thanks for watching, and see you next time.